Witam Państwa bardzo, bardzo serdecznie, tak licznie zgromadzonych, a przede wszystkim pragnę powitać naszego honorowego gościa, Sir Rogera Penrose'a. Welcome to Sir Roger Penrose. Sir Roger wygłosi wykład w ramach Copernicus Center Lectures. To jest pierwszy wykład z tej serii, którą mamy nadzieję kontynuować co roku. Jest to druga część sympozjum, które rozpoczęło się w Warszawie 3 dni temu. Tam w Instytucie Matematyki w Centrum Banacha było dwudniowe sympozjum na cześć Sir Rogera Penrose'a, poświęcone jego dokonaniom w dziedzinie matematyki i fizyki. W tej chwili w Krakowie jest pierwszy dzień sympozjum, jutro będzie kolejny i krakowska część jest poświęcona fizyce i filozofii Sir Rogera Penrose'a. Ponieważ wykład będzie po angielsku, więc proszę mi pozwolić, że ja również przejdę na angielski, żeby nasz gość wiedział, o co chodzi. I want first to introduce our honorary guest. The best witness to his scientific achievement is the fact that in September, 6 volumes of his collected works will be published by the Oxford University Press. 6 volumes of his collected works, and these collected works will contain only scientific papers, both those which already were published and those who circulated among scientific community. 6 volumes of such papers. Books of Sir Roger Penrose will not be included in this collection. The books which are well known also in this country. I am not going to present all Sir Roger's contributions to science. In fact, contributions to many areas of science. I want only to emphasize the fact that he is not only a scientist of a greatest caliber, but also the truly original thinker, and his works, his scientific works, stem from his original vision of the world. And I will also now disclose one feature of his image of the world. In the 12th century, in the school of Chartres in France, and also in Oxford, there was a group of philosophers who claimed that it is not matter, but light, which is the fundamental stuff of the universe. Their doctrine is known among philosophers historians of philosophy as a metaphysics of light. They claimed, those philosophers, that the idea that light is the building block of the universe comes from Plato. In fact, it is not quite true. Roger Penrose, probably without not knowing this, is a continuator of this old but mostly forgotten tradition. Of course, a continuator, a completely new scientific environment. In the theory of relativity and in relativistic cosmology, it is the so-called conformal structure which is responsible for the propagation of light. And exactly in Roger's vision of the world, this conformal structure, well, I will stop at the moment, and I will stop my introduction and let Roger himself tells you the story, his story of the universe and light.
Well, thank you very much, Michael, for that very kind introduction. It's a very great pleasure for me to be here in the city of the great Copernicus, who has obviously influenced the progress of science in unimaginably many different ways. The title of this talk, I don't think I can get it all on this transparency, on this machine, so I have to use this machine for that one. Here we are. The title is Aeons Before the Big Bang. And in order to explain what this title is about, I shall have to give you a picture of how we view the universe, the standard picture of the universe, and I've done it on a picture, in fact. So I don't know whether I can get the whole universe onto this particular slide here, but this is current cosmology, and this picture is what's called a space-time diagram. So we have time going up the picture, and space then goes horizontally across it. I hope you can see this all right. I can't very well see what's up there. And so you have to think of space as starting at the bottom and expanding and expanding. The way this is drawn, you would think that space is necessarily closed. Of course, I can't draw all the dimensions. Space has 3 dimensions, time 1 dimension, and it looks as though I've drawn the whole of space around here, which suggests that the universe is closed. I'm not intending to suggest that. It might be open, it might be closed. Present-day observations are unfortunately just in the borderline between open and closed, and so we don't know is the answer. But it doesn't matter for what I want to say today, whether the universe is open or closed. But you have to realize that this picture, although it looks closed in the picture, that doesn't matter. The main thing is that the universe started according to conventional cosmology with the thing called the Big Bang, represented by this mark at the bottom, some kind of explosion which created the universe. It started expanding, slowed down a bit, and now it's observed to be expanding exponentially. This was not expected by most cosmologists, I think. However, it is implicit in the equations, the slightly modified equations that Einstein put forward in 1917 when he introduced this thing called the cosmological constant. He introduced it for the wrong reason, thinking that it would enable a universe to be static, which is what he wanted, and this was just before the convincing evidence that the universe is actually expanding came about. And so after that, he thought that perhaps lambda was a mistake, and he regarded it as a big mistake that he had made. However, once he had introduced lambda, you find in every cosmology book, at least every cosmology book I know, this lambda is represented. So it's not as though it was a surprise that it existed. It was, however, a surprise perhaps that it really was there and that it was positive. This is essential for what I want to say, that it should be there. So without that, my own scheme that I want to describe would not be possible. Let me say a little bit more about what present-day cosmologists tend to say. What they tend to say is, in this picture, I have rather not exactly left out something important, but I have crowded it all down in here. There is something known as inflation, which you will see, again, in at least most modern cosmology books. You will see the notion of inflation. And the thing is, in my picture, it's not that I have cheated because it should be there. It's just that it would be so small, tucked into this beginning part, that you wouldn't recognize that it was there. So what we have to do to see that is to put our magnifying glass here, and then I think I shall leave that over there and see what the magnifying glass would see, which would be this exponential expansion prior to this one here, so a very early exponential expansion, which was supposed to have taken place in the very early universe. So it would look something like this. There is, of course, what happened right at the beginning, and if I put my magnifying glass over here, you would see something like that. So it's as though the universe had 2 phases of this exponential expansion, and so on. Now, I'm going to confess to you that I'm not really a believer in this one. So although it is standard opinion that the universe had this inflation. I don't believe the initial reasons for it. There are some other reasons that one might believe in this idea. If you don't believe in it, you have to accept other things, and it's these other things which I want to tell you about. But the idea really of inflation, at least one of the basic ideas is the fact that the universe seems to be very uniform on a very, very large scale, and this is a puzzle to people, and we'll see as the talk goes on that it is a big puzzle. But the attempt of inflation is to explain this by assuming that if there were very small irregularities when the universe was small, that because of this exponential expansion, it would smooth the universe out to the kind of regularity that we see now. I want to explain that that reason can't be right. Nevertheless, there are other reasons that one might still support the idea of inflation. And if you don't believe it, you have to supply some other explanation for the things that inflation does for you. So I'll mention this idea even though it will not form part of what I want to say shortly. The main linchpin of what I want to describe is a thing called the second law of thermodynamics. Now, I can't get this slide completely on here, but you could see I have the word mystery here. The second law of thermodynamics is down there. Now, the second law of thermodynamics is, to my mind, two things at once, which are almost opposite. On the one hand, it is something which is almost obvious. What does it say? It says that as time progresses, things get more and more random. So it's a really kind of depressive kind of law. It says things are just going to get worse and worse. That's a little bit misleading, but it does say that things get more and more random. That's not a mystery. The mystery is something else. So let me come to that. Perhaps I'll leave that one on here so you can see what I'm talking about. And to describe the second law, I shall use a cartoon here. Let's take it here. Here we have a picture of an everyday occurrence. Let me put it like this. I'm going to suppose that the laws governing all the particles, you see, our picture of the world is that ordinary things are made up of lots and lots of particles, and you might take a Newtonian picture of what happens. These particles attract each other, repel each other by forces, and there are Newton's laws which would tell you how the particles behave in accordance with those forces. But the thing about these laws is that they are completely symmetrical in time. If you run the clock backwards, the laws will be just equally satisfied as if they are run forwards. So that everything that we see in these pictures would work just as well backwards as forwards. Now you see, I have here something which, a glass of wine perched on the edge of the table, and it falls off, the wine splashes out, and the glass breaks into lots of pieces on the carpet below. Now, as I say, all the laws, this would be completely consistent with Newton's laws. Newton's laws would work equally well in the opposite direction, so it would be just as possible for this to start as the mess on the ground, the piece of glass come together, the glass jumps up in the air, the wine leaps up off the carpet into the glass, and it perches itself on the edge of the table. That's completely consistent with Newton's laws. You might ask, where did the energy come from to get it up there? Well, the energy was already present in the random motions of particles down here. There's no inconsistency there. However, this is a gross violation of what is called the second law of thermodynamics. This second law is telling you that as time increases, this notion of entropy, which is a measure of disorder, as I say, the randomness in some sense, is increasing with time. And if we agree that the second law is supposed to hold, then this progression in this direction would be inconsistent with it. Now, I want to be a little bit more precise about what the notion of entropy is and why we might expect that it should be increasing. In order to be more precise, I want to introduce a notion which is the notion of a phase space. Now, what is this? It's a space with lots and lots of dimensions. I've drawn it here as though it was just drawn on a plane. That's just for ease in picturing it. I hope all that fits on the screen up there. I'm not quite sure what fits, so tell me if it's going off the edge. Each point in this space represents an entire situation in one of these pictures. I have to imagine that, say, there's a zillion particles. If you don't know what the Polish is for zillion, I don't know either. The word, I'm not even sure what it means. It means a very, very large number. It doesn't mean a million or so on. A zillion just means some large number. Now, if there were a zillion particles, you would need to have, for the position of each particle, I would need 3 numbers. How high is it? How far? Well, the 3 dimensions of space would require 3 numbers. I also need to know how it's moving. The velocity, if you like, but what I really would describe this in terms of would be the momentum. So that's the velocity times its mass. That's 3 more numbers. It could be moving in some direction with a certain magnitude. So I have 3 numbers of position, 3 more of momentum. So for each particle, I would need 6 numbers. So that would be 6 zillion numbers altogether. And I want a space in which those 6 zillion numbers describe the coordinates of that space. And that is phase space. So you have to imagine that each point in this picture represents a different thing that might happen to all the particles in the room. Now, I've also drawn some various boxes here, compartments. Those are what are called coarse graining compartments. And the idea of these is that if you have 2 points in the same compartment, they represent 2 situations which look the same. Now, look the same is a bit vague, but the notion is slightly vague, but not too bad. The idea would be that you take, say, the gas in the room, you ask what is the chemical composition of that gas, what is the temperature of that gas, what is the motion of it, and so on, the pressure, various macroscopic parameters like that. And if you know those macroscopic parameters, you know pretty well what the gas will do. Likewise for the wine in the glass, for the material in the table, and so on and so forth. All these things will be described by overall macroscopic parameters, but there are lots of different ways that the individual particles might be organized in order to give the same macroscopic parameter. And all these things in the same coarse graining region would be the things with the same macroscopic parameters, but where the details of the individual particles might be quite different. Now, some of these will be much bigger than others. And in fact, the big ones are likely to be stupendously bigger, much, much, much bigger than the small ones. That I can't very well indicate in this picture, because not only do I not indicate all the dimensions, I don't very well indicate the extraordinary difference in size between these coarse graining regions. Okay, well, what's the entropy? These regions will individually have a volume. And the volume is this thing V here. This is a formula due to Boltzmann, and it really made sense of the notion of entropy. Okay, there's still a bit of vagueness, but it was much better than anything that went before. So here we have V. The thing called S is the entropy. K is the thing called Boltzmann's constant. It's the only thing in this formula that was not due to Boltzmann. I think it was not due to Boltzmann only because he never bothered to write it down. But he certainly knew the idea. This is just an ordinary logarithm. Well, log to the base e, don't worry about it, doesn't matter much. It's a logarithm, and this is the volume. So the volume of the coarse graining regions, for example, let's suppose this initial picture was described by a point in the yellow region here. The volume of that yellow region would be the V appearing here if we want the entropy of that. So roughly speaking, it's the logarithm of the volume, which is the entropy. Now, volume, of course, is a volume in 6 zillion dimensions. It's not ordinary volume because we have all these coordinates. But don't worry too much about that. So the idea is that as time progresses, the point representing what happens will move around in this phase space. And that describes exactly what's happening here. Now, you see, I did say that these volumes were vastly different from each other. So whatever size this one is, there's likely to be a much huger one next door. And the chances are where it will go into this much huger one. And it's so much huger that once it gets into the bigger one, it's hardly likely to find one as small as the one it came from. Now, the thing is that Boltzmann's constant is pretty small in ordinary terms. More important, the logarithm makes huge differences, very small differences. So that a very small change in the entropy will represent a very vast change in the sizes of these volumes. But we've more or less seen why the entropy should increase, because whatever the size of this is, the next one is likely to be absolutely stupendously larger again, and this is just the way things, just the likelihood of what will happen. So we will understand that if the entropy has some particular value now, it is almost certain to increase in the future. And that explains, if you like, the second law of thermodynamics. Or does it? The thing is, you might worry a little bit because, well, didn't I say Newton's laws were symmetrical in time? And we seem to have deduced something which is asymmetrical in time, grossly asymmetrical. It says that this thing called entropy is increasing as time goes on. So you might ask, where have I cheated to explain something asymmetrical in time from laws which are completely symmetrical in time? Well, the way I've cheated is only in the question I asked. I said, if it starts off like this, then what it will do in the future is very likely to be that. Let me ask a different question. How did it get there? What is the most probable way that this glass appeared on the edge of the table? Well, we can go back to our phase space picture and say, okay, it found its way in this region. What was the most probable place it came from? Well, you look around and you see a bigger volume. Oh, yes, it's much more likely to have come from the big volume, and it's much more likely to have come from a bigger one than that. So what we seem to deduce is that in the past also the entropy would have gone up backwards in time. In other words, it came down with time, which is the complete reverse of the second law. It's completely wrong. For example, it would tell us that the most likely way the glass found its way at the edge of the table is that it started as a mess on the carpet with broken glass. The broken glass assembled itself, jumped up in the air, and the wine jumped into the glass, and it perched itself delicately on the edge of the table. Well, that's completely wrong. The right answer, of course, is that someone who had been drinking a little too much of this had staggered up to the table, perched it on rather carelessly on the edge, and that is more likely what actually happened. That would be consistent with a curve which was consistent with the second law, with the entropy going up. No matter how drunk that person was, that person would have had an entropy that was relatively low, and this is the true thing that happened. It's by no means explained by the discussion I've given you here. There's something else going on. This discussion only works if we assume everything is sort of random from there on. There was something, in effect, which was pulling this curve down in the past, pulling it down and down. What was it? Well, here's an advantage with the way this thing is arranged. I can add my other transparency to this, and you can work your way back, and it kept on going down and down in the past, in other words, consistent with the second law, until you get to the Big Bang. So what this is telling you is that whatever the Big Bang was, it must have been a state of very, very small entropy, a highly organized state in some sense. Now, what about the Big Bang? How do we know it was there? Do we really believe in the Big Bang? Well, there is a lot of very good evidence for the Big Bang, and one of the most important pieces of evidence for it comes from what is referred to as the microwave background radiation. This is microwave radiation, electromagnetic radiation, photons, if you like, coming to us, and it is understood, the way it's often described, is as the flash of the Big Bang, cooled down by the expansion of the universe. It's not very hot now because of the expanding universe, and now the temperature of that radiation is about 2.7 degrees absolute. That is 2.7 degrees above absolute zero. Now I'm going to talk about two particular important features of the microwave background. It's very important to cosmology. On two quite separate occasions it won the Nobel Prize. So let me show you one of the things I want to say. This is a curve here. There's a continuous black line, which is a theoretical curve. I'll come to that in a minute. And there are some error bars here. Now, what these describe are, this graph is, in this direction, the frequency of the radiation, And this up here is the intensity. So the radiation is composed of different frequencies, but this shows you how much of each frequency is involved. Now these are error bars for the actual observations. I suspect nowadays they have better pictures than the ones I've showing you here. This is a little bit old, but never mind. It's good enough for these purposes. You'll notice that these error bars are quite close to the curve, but it's more than that because they're exaggerated by a factor of 500. This means that the real error bars are 1/500th of the length of the bars you see here. So even the worst one, right at the end here, is so accurate that if I shrunk it down by 500, it would be inside the thickness of the ink. So it's a very, very precise agreement between the theoretical curve and the observations. Now, what is the theoretical curve? This is the well-known, famous Planck curve. Max Planck gave an explanation for this, which started off quantum mechanics at the year, 1900 was the year of his paper. This was referred to as a black body spectrum. What is a black body spectrum? Well, really, it's telling you what's called thermal equilibrium. What it means is that what you're seeing is radiation coming from something thermal equilibrium. Well, what does thermal equilibrium mean? Well, you'll see actually in my picture here, I have the words thermal equilibrium. They describe the largest region of phase space. In fact, it's usually so large that it's bigger by far than all the others put together. What does that mean? It's by far the largest region, the largest entropy that you could have in the situation under consideration. So here it would represent the maximum entropy state that could happen in that room. And you see that's where, if you leave things to their own devices forever, ultimately they would end up. Now there's something a bit strange about this. I thought I was going to go back to the Big Bang and find in some sense a minimum entropy. What have I done? I've found a maximum entropy. That's what this curve is telling us. So there's something very odd, and I often puzzle about why, not just about the phenomenon, but I puzzle about why cosmologists don't worry more about it. Because it seems to me this is a really great puzzle. As I've stated it, certainly. And I think there is in the backs, or at least there used to be in the backs of their minds, something like, well, in the old days the universe was very small and there wasn't much room for much entropy, so that's why it was so small. That's just wrong. I don't want to go into details of why it's wrong. I think I'll better just explain what I regard as the correct answer. The correct answer is that this curve is not looking at everything about the Big Bang. It's looking at the photons coming from a collection of photons and matter particles running around at random in thermal equilibrium. What it's not describing is gravity. And gravity, according to Einstein, has something to do with the geometry of space-time. So it's not describing that geometry in some important way. And I want to come to my next slide here to try and indicate what I mean. In discussing the second law of thermodynamics, it's quite often, one would talk about a gas in a box. Now, for this, you might imagine that the gas was initially in one corner with some compartment walls to wall the gas off from the rest of the box. You then remove the walls, and the gas will tend to spread itself over the whole box. And that represents an increase in the entropy. Now, that's perfectly all right. Entropy increasing, time getting later and later. Now, let's suppose, on the other hand, that this is not a gas in a box, but we'll have an absolutely huge box, and these points here represent stars. So it's an enormous galactic scale box or something, just in your imagination, and these are stars. And then you will find there's a tendency in the opposite direction, that they start to clump. Because of gravity being a universally attractive force, means they will clump together, and as they clump, this situation looks almost like the opposite of what's going on here. Now, there's another feature of the microwave background which is just as important as this, which is, this is just, if you look at any one point, you see this spectrum. But in fact, if you look all over the whole sky, you find that the temperature, where this peak is here has something to do with the temperature, that the temperature of that radiation is almost exactly the same over the whole sky. It's so close over the whole sky that it's something like to about 1 part in 100,000. That the temperature is equal all over the sky. So that's something else it's telling you, which is that the universe is pretty well uniform. So at the Big Bang, the universe was indeed very uniform all around. So if we look back at this picture here, you see, yes, that's consistent with this, but as far as gravity is concerned, it's telling you that the entropy was actually very low. What we're seeing is a combination of this and this, a combination of those two pictures, and that is, as regards to the matter, yes, high maximum entropy, that's consistent with the shape of this curve, but as far as gravity is concerned, very low entropy. In fact, this is very important to existence of life on Earth. I think I'll put this one on the other side. Because, well, how does life manage to operate on the Earth? Well, because of the sun. That's certainly correct. What's less correct is the idea that what the sun does for us. What good is the sun to us? Well, the usual answer is that it gives us energy. That's not quite right. Why is it not quite right? It's not quite right because we don't actually get energy from the sun, because the energy coming in the daytime, throughout the course of the day and night, will simply go back out again. If it didn't, the Earth would get hotter and hotter and hotter very rapidly. Of course, it may be getting hotter and hotter because of global warming, but that's relatively small on the sort of scale I'm talking about here. It wouldn't be any colder at night. I mean, as the night went on, it wouldn't get any colder, and then the next day it would just get hotter again. That's no good, because all this energy escapes back into space. The key point is that the sun is hot and the background sky is cold. If the background sky were the same temperature as the sun, imagine the heat of the sun all over the entire sky, that would be completely useless. But what's useful to us is the combination, the contrast, if you like, between the hot sun and the dark sky. Now, what does that do for us? Well, because the sun is hot, that means that the photons coming from the sun are, on the whole, higher frequency photons, a yellow light. What goes back is sort of infrared. That's low frequency. And according to the famous formula of Planck, which came into that curve I just showed you, according to that famous formula, each photon has an energy which is proportional to its frequency. So this means that for high-frequency light, you don't need so many photons, because each photon is more energetic. For low-frequency light, you need lots more photons. Fewer photons coming in, lots more carrying the same energy going out. Fewer photons means fewer degrees of freedom. Fewer degrees of freedom means smaller entropy. So this entropy here, that means smaller volume here. Low entropy light coming in, high entropy energy going out. And the plants have developed this skill of using the fact that these are high-frequency photons, lowering the frequency to the visible light sort, to the infrared light sort, and using the entropy in that photon to build up its substance. And then animals eat plants, and we eat animals and plants. And what we get from the sun is the capability of keeping our entropy down. That's the key thing. It's not energy. If we gained energy, we just get fatter and fatter, which is not so much use to us. It's more useful to be able to keep the entropy down, and that's what we do. Now, what does this have to do with the discussion I've just been saying here? What it has to do with it is, you might ask, why is the sun a hot spot in a dark sky? Well, the key thing is that it's there at all. Okay, you could say it's thermonuclear reactions which are making the sun hot. That's a bit misleading too. It's certainly true, but if if there were no thermonuclear actions, the sun would still be hot. It's just that it wouldn't stay hot. It would shrink down and it would get hotter and hotter, in fact, but it would cool off then. Or, well, never mind. What would happen to it is actually something more like what I'll say shortly. But the key thing is that the sun is there at all, and it's condensed out of a previously uniform distribution of gas. So it's this process going on, which has been made use of the sun. It's the potential to concentrate the matter, which was there because the universe was uniform earlier. And so it's this reservoir of low entropy in the gravitational field, which is made use of. So that is the thing. That's why the sun is there, and so on. Now I want to say something else about this picture, and I suspect I better do it this way around. Here we have a thing called a black hole. The black hole comes about when the concentration of material is at its maximum. And I want to draw you a picture of a black hole. And again, it's a space-time picture. It's not what you would see as you looked at the black hole. Well, it's indicated here, but this is a space-time picture. And here we have time going up again, as before. Here's time going upwards. So you think of down here is some old star which has used up all its material for keeping it warm, and it eventually collapses, goes down. And as it collapses, it gets smaller and smaller, and its gravitational field starts to become stronger and stronger because it's so concentrated, and this causes these things called the light cones to tip over. So to understand this picture, you're going to have to know what light cones are. So I have them on this slide here. Here we have a light cone on the left-hand side. This is a configuration in space-time. The light cone is what would happen if you had a flash of light occurring at some point. It then spreads out. See, as time progresses, you can think of this as a slice through the picture, so you can imagine what happens when time progresses. Right down here is where the flash of light occurs. In this picture, it's represented by that point in the middle. A moment later, that flash has got to this region. That's here over here. And then a moment later still, that's right out here. I've been able to draw it as though it were spherical surfaces, which is what you have to imagine. I can't very well do that over here in my space-time picture. I haven't got enough dimensions. You have to imagine that these things which look like circular sections really represent spheres. But that won't matter too much. The dimensionality is good enough to get the general idea of what I'm talking about. There is the past cone, which is labeled by a minus sign here, which is you imagine a flash of light converging on that point. The future cone is the flash of light expanding out from it. You have to think that at every point of space-time, there is one of these cones sitting there. There doesn't have to be any actual light doing it. It just describes the geometry of space-time. Now, there are two kinds of relativity, really. One of them is special relativity. That's the initial form. The idea of representing this in space-time in this way was actually due to Minkowski. And when Einstein first heard about it, he was not very pleased with the idea. It took him a little while to get used to it. And then when he was used to it, he realized it was actually an extremely good idea. But the idea is that you represent the time and space all together in one four-dimensional picture. It looks three-dimensional here, but that's all right. And there's a light cone at every point. Now, photon, that means a particle of light, if you like, is something whose world line, that represents the history of that photon as time progresses. That photon is a world line which is always tangential to the cones. It always runs along the cones. So it goes with the speed of light all the time. Whereas a massive particle, an ordinary particle with mass, would have a world line. Its history would then be represented by this world line, which is always within the cones. It's not allowed to go faster than the speed of light, so it has to have a world line within the cones. This still applies when we go to general relativity. It's just that the cones now can be all over the place. They don't have to point uniformly. And you see in this picture over here, I have an example where the cones are not arranged uniformly. But it's still the case that photons, light particles, must travel along the cones, massive particles within the cones. And you see here the cones start to tip over as an effect of the gravitational field, and there is a place where they've tipped over so much that in the picture one side of them is vertical. And this has the effect that if anybody unfortunate enough or foolish enough to have fallen within the horizon, as it's called, this is where the event horizon, which is where the cones have a vertical side, it just becomes impossible to escape. Because if you were trying to escape, at some point you'd have to get across the surface, and you can't do that without violating the law here that your world line has to be within the cone. So this describes what's called the event horizon. An external observer looking in, the light that escapes also cannot have ever been inside this horizon. The other feature about this picture, which is important, is the singularity in the middle. This is a place where space-time curvatures have become infinite, where densities have become infinite. This poor collapsing star here is squashed to an infinite density. Whether that makes any sense, well, we'll think about a bit. But in the mathematical picture of this collapse, you have in the middle a singularity. Now, this singularity reminds one of what we've already had in the case of the universe as a whole. There we had a singularity again. This was the Big Bang, where densities became infinite, curvatures became infinite, and if you extrapolate backwards here, you find this singular state where all the equations that we understand of Einstein and so on go wrong. And so you have these two problems. They're sort of complementary problems. You could have the beginning of time. This is the sort of picture, the normal picture of the Big Bang. It represents the beginning of time. And locally, for any poor or unfortunate person having fallen in the black hole, you find, again, a singularity representing the end of time. So we have these two ends of time, in a sense, and these are the singularities. I should make this picture more complete now by putting in the black holes. So these singularities that we have over here now must be represented on our picture. So these now are black holes. You may have various black holes congealing with each other and so on, but they should be represented in our picture. I don't know how much of that shows up there. I guess that's okay. Right. Now, what about the second law of thermodynamics? You see, there's got to be something very special about the Big Bang, which is not special about these singularities in a black hole. This is the sort of thing which will just happen by itself. Entropy is going up and up and up and up, increasing enormously when you get inside a black hole. In fact, that's the major contribution to the entropy in the universe is from black holes. Now, I did talk about inflation a bit before, and it was supposed to be an explanation for why the universe is as uniform as it is. I want to try and explain to you why it's not an explanation of that. You see, here we have this picture of the history of the universe. What I want to do is to imagine that the universe is collapsing. You only have to imagine it. It's not going to do that on us, as far as we know. Now, in general, you would expect also there would be a bit of irregularity in the matter distribution in this universe. And that irregularity, as the universe contracts, will be more and more likely as time goes on to form black holes. Now, these will be described in this picture here. These black holes will represent high entropy, very high entropy situations, sort of general, highly random, if you like, situations, and they will start to congeal and produce an incredible mess in the end. So here we have time. Now, I managed to make time go the other way. Time progressing up the page still, and you see this thing that's sometimes referred to as the Big Crunch. Now the question is, that is a much, much more likely situation, far more likely, we'll come to how more likely shortly. Why didn't the universe start off like that? That is a much, much more likely situation to have been the beginning universe. Okay, was it inflation that stopped this? It can't really have been, because I can put into the equations of general relativity, the equations of all that we know about, I can put those equations that cosmologists like to put in if they want to have inflation. There's a thing called the inflaton field. It's just a strange, rather contrived field, but it satisfies the same kind of time-reversible laws as any other physical field. And so if you put the inflaton field in, you still get this picture. It doesn't explain why the universe did not start like this. In fact, that would be described by what's referred to sometimes as a white hole. If the time is going backwards this way, you get what's called a white hole. Now, we don't expect to see these things in the universe for a very good reason, because they grossly violate the second law of thermodynamics. See, black holes are things for which the entropy continues to go up, and it's very, very consistent. There's a lot of very wonderful results to do with black holes, which are all consistent with the entropy increasing in the normal time direction where you have a black hole. If you turn time the other way around, you have a white hole, completely goes against the second law of thermodynamics. So we don't expect to find white holes. We don't have any evidence at all that they're there. We don't see any evidence of the irregularities which would be present were there any white holes in the early universe. They just were not there. Okay, the black holes were there, but not the white holes. Now, I want to try and give some possible insight into why there were no white holes. But first of all, we have to understand what is special about the Big Bang. This is just a little bit of a sort of mathematical problem. How do we characterize what is peculiar about the Big Bang? Don't ask why it was like that, just try to find a characterization. Well, actually, I should say my slide over here is asking the question why, so let me put that down here. It's a fundamental problem raised by the second law of thermodynamics and the nature of the Big Bang. Why did the Big Bang not involve any white holes? That's the time-reversed black holes. And it's not answered by inflation or by any current theory of quantum gravity. I should say quantum gravity because it's a standard view that if you want to understand what the Big Bang is like and why it was like that or something, you bring in quantum gravity. Quantum gravity is the missing theory which is supposed to unite quantum mechanics and general relativity. That's fine. The only trouble is that every quantum gravity theory that I know is also symmetrical in time. So how on earth is that going to explain why the Big Bang was so special? So we have a real conundrum here. But let me come to that conundrum in a moment. First of all, let me address the question of what it was that was special. I'm not quite sure whether I can do this on this side, but let's try it. In order to talk about gravity and ask the question, in what way was the Big Bang special? It's a gravitational question because it was gravity that somehow was not taking part in the thermalization that everything else seems to have taken part in it. But I want to compare gravity with electromagnetism. Here we have the observations primarily of Faraday, although lots of other people before him, and the theory due to Maxwell, which is a very beautiful set of equations which describe how electric and magnetic fields intertwine with each other and how they behave in accordance with their sources. So I want to have a picture here. First of all, in red I'll have the field. In this case it's the electric field, and the source is in blue. That's the source, that's an electric charge. So you have an electric charge here, it will cause an electric field. The field is outside, the charge is in the middle here. Now I could have had instead a magnetic field produced by current. So I could have a current going around a loop, causing a magnetic field. Now Maxwell's theory combines electric and magnetic fields together into one entity, which is quite usually called the electromagnetic field, and the letter F tends to be used. It stands for field, I suppose. The electromagnetic field is described by this thing. It's a tensor, don't worry too much about that. Just think of it as a thing called F. J is the thing which represents what's called the charge current. It's called the charge current vector. So it encompasses both the charges and the current. And it's the source. So the blue thing is the source, the red thing is the field. Now I want to try and do something similar in the case of gravity. And I've left the space for that. in the case of gravity. Again, now the names of Newton and Einstein come to mind. And the source, in this case, will be mass, and the field is the gravitational field. In fact, there are two kinds of field again, the magnetogravic and the, or whatever you call it, the electrogravic. Forget it. There are two kinds, but they all combine together into one object. So we have an object describing the field and another object describing the source. And these are things which are called tensors, and don't worry too much about the names here. I just want you to make the comparison. The thing called C is the Weyl curvature tensor, which is the analog of the Maxwell field tensor. The thing called R is the Ricci curvature tensor, and that's the analog of the charge current vector. So that's, for the moment, what you need to know. One thing I'm going to say here, which we need for later, which was in Maxwell's theory, you have, this is one of the great achievements that Maxwell made, was to explain the behavior of light as magnetic and electric fields which sort of propagate each other through space at the speed of light. And that became a magnificent explanation for what actually light is. There is an analog of that in the gravitational case. It's just called gravitational waves. They are known to exist, but somewhat indirectly. There are systems can only be explained, their dynamics can only be explained by the fact that they do indeed emit gravitational waves exactly in accordance with Einstein's theory. So we believe them to be there. Okay, that's coming in later. For the moment, I want to do something else, which is to give you some kind of a picture of what the gravitational field looks like. I say looks like deliberately. Suppose you wanted to see a magnetic field. It's a good way of doing that. You just take, say, your magnet, and you take a piece of paper, and you sprinkle iron filings, and they all line up nicely, and you can see almost the magnetic field. You could do a similar thing with the electric field with pith balls or something. So these things, if you have the right sensor, you can see them easily. Now, what about the sensor in the case of the gravitational field? Well, here, you can, and I want to try and describe that. I think it will be all right to do this here. I'll put that up there. This, in fact, was the first serious observation confirming Einstein's theory that Eddington made this trip during an eclipse to the island of Principe to have a look to see whether, as Einstein had predicted, the star field behind the sun would look as though it was distorted. This is due to the following effect here. This is a space-time picture again. This tube here represents the history of the sun. Some two distant stars down there and an observer here. And the light coming from these stars, according to Einstein, is bent slightly by the presence of the sun. Of course, you can't very well see stars when you're looking straight at the sun, so the idea was to wait till there was a good eclipse and then have an expedition to see whether the star field was in fact distorted in the way Einstein had predicted. So you see, because the light is bent inwards by the gravitational field of the sun, the image, two stars which are this far apart, if the sun hadn't been there, they would seem to be this far, but because the light is bent inwards, they appear to be further apart if you extrapolate these lines back here. So what the sun does is kind of push the star field out. That was the prediction, and this, I've described it slightly differently here. You see, I'm describing it in terms of these two kinds of curvature, which affect the distortion of light rays. The sun itself, if you could see straight through it, and forget about refractive indices and forget about the brightness of the sun and so on, imagine you could just trace the light rays through the sun, then it would look like a lens. It would look like, well, we've had this lens already. I could bring it back again here. This lens here. It would look like an ordinary magnifying lens. And that's the effect of the Ricci tensor. That's the source thing here. That's the blue one. So that would be the magnification. But that magnification, of course, you can't see it because not only can't you see through the sun, but the moon's in the way too. So that's much good. The moon has to be in the way for you to see the other stars. So, but nevertheless, it pushes the star field out it pushes it out less and less as the further you go out, which means that it introduces a distortion. Suppose there happened to be a circular pattern in the sky, that distortion would stretch it out and make it look more elliptical. So, and the further out you go, the less the effect would be. That distortion is the Weyl curvature. That's the gravitational field. That's the analog of the iron filings. So this distortion effect, as I've tried to indicate in this picture here, is the Weyl curvature. Here we have indication. The magnification is the Ricci part. That's the source. The Weyl part that you see outside it, that's like the analog of the iron filings. Now this is something which actually can be seen, and it's become an important observational tool in astronomy. Now I'm not sure whether you can see these pictures very well. I can't see at all down here, so you'll have to trust me. I hope you can see it. Somewhere out here, oh, thank you. Somewhere out here is you see, the trouble with galaxies, I should explain that there is something in the intermediate field down here, and most of the galaxies you see are much, much, much further away. So those are playing the role as the stars that Eddington was looking at, and this is sort of playing the role of the sun. So what that Weyl tensor field should be doing is distorting the images of the galaxies to make them look elliptical. Now, one of the troubles with the galaxies, of course, is that they already tend to be rather elliptical, so that means that if you just see one image, you wouldn't know whether that had been distorted or not. So what you have to do instead is a lot of very clever statistics, and you see whether there's a general tendency for them to be stretched out in certain ways. And that's what people do. But if you're lucky, you might even just see it. So you may see, and I'm not so good at seeing this anymore because I've seen this picture too many times, that there is a kind of stretching out around there, telling you that there is a big mass in the middle here which is affecting the very distant galaxies and stretching them out in that way. I hope we can see the next one perhaps a little more clearly. I think it's best if I use this picture here. I hope you can see that. There you have a general stretching out of the kind which I was trying to indicate on the other side there. And you can see there are these stretched images, and if you just saw one or two of them, you might think that really was a pretty stretch, just a sort of long, thin galaxy or something. But you can see there is this general tendency, which is indicative of a very big central mass down here. If you don't believe these pictures, I can even show you a more extreme case here, where you have, in this part of the picture, something stretched out in a completely impossible way, if it were really like that. It's an image of some perfectly reasonably shaped galaxy. It might be a little bit elliptical, but certainly not stretched like this. The stretching out is due to the mass in the middle here, which has distorted that distant image and enabled you to see the Weyl curvature in this intermediate region. So you can actually see this gravitational field. Okay, that's just to give you a feeling for it. What I want to do next is to try and tell you what we have to do for the Big Bang. As I said, this is just a way of characterizing it in a nice way. The Weyl curvature hypothesis, it's something I suggested some years ago, is that the Big Bang must have been subject to a huge constraint, to a region of phase space which is very, very tiny. You see, you remember my phase space pictures, which I probably can't find anymore. Here we are. So the way this point must have started out is a very, very tiny region representing very, very small entropy, a very, very tiny region. How tiny was it compared with the whole phase space? Something like, no bigger than, 1 part in 10 to the power 124. It's such a tiny pinprick, you certainly wouldn't be able to see it on that picture. Well, you see, I've written this as a double exponent. If I wanted to write this as 1, 0, 0, 0, 0, 0, 0, like that, I would have had to have 10 to the 124 zeros. That many zeros, I certainly couldn't get onto the page. I couldn't even fit them into the universe if I put 1 0 on every single proton within the observable universe. That's not nearly enough. So that gives you some idea of how vast that phase space is in relation to the tiny region that the universe had started off from. So you really need an explanation. Well, maybe you say that was just put there by some act of something or other, but I think we need something a bit more scientific. So the idea is, I'm only just trying to characterize it now, the idea is that the specialness of the Big Bang appears to be only in gravitation. That was the key point I was getting to here. And it seems to be that the Weyl curvature, that's this distortion curvature I've been describing here, appears to have been zero, or very close to zero, at the Big Bang. And that gives you this very, very tight specification to 1 part in 10 to the 10 to the 124, something like that. Whereas in the general case, such as in black holes, it diverges wildly. So this hypothesis, the Weyl curvature hypothesis, applies to the Big Bang. It does not apply to the time-reverse type of singularity you find in black holes. Now, that condition, as I phrased it, is a bit awkward. It's a bit awkward for lots of reasons, but one main reason is that this thing called the Weyl curvature tensor, it's a tensor. Now, I haven't told you what a tensor is, but if you know anything about differential geometry, you know it's not a very nice notion if you want to say what it is at a singularity. You need a nice smooth space to say what a tensor is. So what is to say it's zero at somewhere where it doesn't exist? Doesn't make much sense. Okay, you can think of clever mathematical ways of saying this in terms of awkward limits and so on, but a much better way of saying it is one that has been promoted by my colleague Paul Todd, and he's done a lot of good work on this to see what kind of a characterization it is. The idea is that you say something a little different. What you say is that the universe, near the Big Bang, can be stretched out. Remember, I could draw these light cones all over the place. Now, what I want to do is draw them, but think of the Big Bang as stretched out in a picture, which I can do. And it's the same picture that I had here, if you like. I stretch it out there in such a way that the light cones still make sense. Now, the thing is about this is that Einstein's theory of general relativity depends on something known as the metric. Now, the metric is something which gives you lengths, if you like. It gives you times. That's the more important thing it gives you. And I have here a picture which tells you what the metric does. Here we have our old friend the light cone, telling you how light behaves. But what about massive particles? Here I've got one zipping through this point here, another one zipping along at a completely different speed. Now, they're both meant to be clocks. The brown clock and the green clock are identical clocks. And here, this is where they start. 0th tick, there's the first tick, the second tick, and the third tick. The green clock, the first tick, the second tick, and the third tick. And according to relativity, once you've got the light cone, the only thing you need in addition to that is to know how crowded these bowl-shaped surfaces are, which represent the different ticks of the clocks. Now, the metric in Einstein's theory is usually called a thing called G or GAB or GIJ or G mu nu or something or other. The point about it is that it has 10 components. There are 10 numbers to tell you what this metric thing is at any one point. 9 of those numbers are telling you where the light cone is, how squashed it is, which way it's pointing, and all those things. Those 9 numbers tell you the light cone. There's only one number left to tell you how crowded are those bowl-shaped surfaces. So the picture that Einstein's theory gives us is slightly incompletely described by what I showed you before. That is this picture of all the light cones. Yes, the light cones are fine, but we need also the bowl-shaped surfaces. So this light cone here, I need to put them in the picture, and likewise, I need to put them in here too. Now that completely describes Einstein's metric. So I now have the structure that Einstein needs for his general theory of relativity. And each point there will be a metric tensor which has 10 components to describe its nature. If I remove the bowl-shaped surfaces, I only have 9 of them, but it's almost all the structure that Einstein used. It's not quite the whole structure. This is the thing that Mikhail referred to earlier, called the conformal structure of space-time. In relativity theory, you can call it the light cone structure. It's really nice. You can do that. It's most of the structure. And in fact, certain things in nature are only interested in that structure. They don't need the bowl-shaped surfaces. Most importantly, something that doesn't need the bowl-shaped surfaces is Maxwell's electromagnetic field. Maxwell's equations don't require the full metric. They just require knowing where these light cones are, and that's the whole story. But what about the extra piece of information? Well, things that need that are things with mass. In fact, it's very fundamental to physics of the 20th century because there are two famous formulae. These two famous formulae, well, Einstein's E equals mc squared, everyone has heard of here, I'm sure. But the other one I mentioned earlier is Planck's E equals h nu, even simpler. It's one fewer symbol, you see. So E equals h nu tells us that if you have a particle, well, let's go to Einstein's one first. If you have a particle whose mass, whose rest mass is m, then that gives you an energy that particle has, an intrinsic energy proportional to its mass. This is just a constant, of course, c squared. Planck says that if you have an energy of a particle, that is completely proportional to a frequency. Okay, there's another constant. This is Planck's constant here. Put these two formulae together, that tells you that a particle of rest mass m defines a frequency, nu, simply in terms of these constants. What that tells you is that particle is a little oscillator, like a little clock, if you like. It's a little oscillator which oscillates at a very specific rate proportional to the mass of the particle. So that's of course, you couldn't use an individual particle to build a clock because it's hard to get this oscillation frequency out. So if you actually build a clock, well, there are very accurate clocks now, nuclear clocks, well, atomic clocks or nuclear clocks, which are extremely accurate, and these depend ultimately on rest mass. They depend on the fact that it's made out of particles which have mass. If you didn't have any mass, you'd have something like Maxwell's equations, and the thing would just fall apart, and you couldn't build a clock. Now, specifically, let's see where I've got to with my transparencies. I must have put down the one I was just talking about. Here we are. Let's go back now to the Big Bang. I said you could stretch this out. See, what I'm saying is that if you just take the light cone structure, you just take the structure of the conformal structure, not the full Einstein structure, then that's the light cones. So you can have a space-time, which has a sort of beginning here, and the condition that Todd introduced in order to characterize the Weyl curvature hypothesis in a very nice geometrical way is to say that, and let's cover this up just for the moment, to say that the space-time would have a nice smooth edge to it, which you could extend behind it. What that's to say is that, okay, you just pretend, this is a mathematical trick, there's not meant to be any physics here, it's a mathematical trick. You say the characterization of the Big Bang, the Weyl curvature hypothesis in this nice way, the characterization is to say that this space, with the light cones painted on it, could be extended to before the Big Bang in a nice smooth way so the light cones just keep going. It's not saying there's anything before the Big Bang, it's just saying this is a nice mathematical trick to characterize the Weyl curvature hypothesis. However, you might wonder now, is it more than a mathematical trick? Now, a reason for thinking that is that how on earth do these particles know where the Big Bang is? You see, when you get close to the Big Bang, the major thing about it is it's enormously hot. Enormously hot means that the energies of particles are absolutely vast. They get so enormous that the mere fact that they have rest mass becomes totally unimportant. The particles behave as though they were massless. And if they're massless, then they don't care where the Big Bang was. So they might just say, to these massless entities, there might have been something before the Big Bang. Well, that's what it says down here. Is it just a mathematical trick? Temperatures get so big that somehow the massless particles would be just as happy if there was something before the Big Bang. That's not a very scientific way of saying it, but that's the sort of thing I mean here. But if there was something before the Big Bang, what on earth was it? I think the sort of tendency most people might have is to say, well, maybe there was a collapsing universe before the Big Bang, and then it bounced and went out again. And a lot of quantum gravity people would try to take that view. I don't think that's a very sensible view if you want to have the second law of thermodynamics. Because, you see, this law here is telling you how special the Big Bang was. If it was a collapsing universe before that, it would have to aim itself to this extraordinary, special, not that great mess, which I showed you in my transparency here. This mess here wouldn't work. You couldn't glue that on this side here. You'd have to have a nice one like this. But if you've got that, how does it produce that from a general initial collapse? It doesn't help you. So let's try something else. What I'm going to try is that what happened in the remote future might have been something of interest to us. So let's take the other end of time, the remote future. Now, what do we expect in the remote future? Well, remember the universe is doing this exponential expansion, and you can do the sort of trick I was talking about, a much older trick than the Todd trick here, that we squash infinity down and make it a nice smooth surface. And you can do that. You can do that provided what's left in the universe is pretty well things without mass, again, so they have no way of making clocks and so on. So that's the basic idea. You might ask what's likely to be around in the very remote future. Well, there'll be all these black holes that seem to be in the centers of galaxies, some absolutely vast black holes. Some of them are about 10 to the 10 times the mass of the sun black hole. Our own galaxy has a black hole of about 4 million solar masses, but you've got the bigger ones in other places. What happens to black holes? Well, according to Stephen Hawking, a black hole, if left to its own devices, it radiates. It's not completely black, he says. And I believe him. So this radiation comes out from a black hole. I should say that it's not very hot, a black hole. In fact, if you take a black hole, I think, if I've got the figures right, about the smallest type of black hole we know might be out there, the smallest one that a star might individually collapse into, it would have a temperature that is something like the coldest temperature ever made on the Earth. If you have bigger black holes, like the ones I referred to in galactic centers, they would be far, far colder. So you might say, well, who cares? Well, if you wait long enough, this universe keeps on expanding, cooling and cooling and cooling, and after a while, the temperature the ambient temperature in the universe gets smaller than that of any black hole you might consider. And when it's smaller than the temperature of the black hole starts to radiate out. This is, again, the second law of thermodynamics in action. It radiates outwards, and as it radiates away, Einstein's E equals mc squared, the energy gets carried away, the mass also gets carried away. So the black hole gets less massive, less and less massive. In the process, it gets hotter and hotter. As it gets less massive, hotter and hotter and hotter. Eventually, it disappears with a pop. Now, I'm calling this a pop and not a bang, because if it went off in this room, okay, I guess a lot of us may just about survive, I should think. It would be rather nasty, but from the astrophysical point of view, it would be nothing. This would be a very, very small explosion. It doesn't matter how big the initial black hole is, it would be the same sort of pop, not much of an explosion. And the biggest ones that we can know are present in huge black hole in galaxies, huge black holes in galaxies, they would take something like a googol years. What's a googol? That's 10 to the 100 years. So it's an awful long time, but nevertheless, eventually they go pop. Well, it seemed to me this is one of the things that I was sitting around about 5 years ago and being rather depressed with it by this idea. You see, here we have the remote future. I put the black holes in, and now I put them going off pop, you see. I've got written up here the boring era. It is incredibly boring. What's going on in the universe? Well, you see, I couldn't think of much more boring than sitting around waiting for a black hole, wait for 10 to the 100 years for that thing to go off pop, and it's pretty much of an anticlimax when it does. So that's the best we can think of for the remote future. That's pretty boring. And then after they've all gone, that's really boring. So then I thought, well, who's going to be around to be bored by all this stuff? Certainly not us. Nothing really, except things like photons. And it's very, very hard to bore a photon, you might imagine. It's hard for lots of reasons, but one of them in particular, because here's the photon going along this light cone. It never even makes its first tick. So as far as a photon is concerned, eternity, as an American would say, eternity is no big deal. So, okay, it's not such a boring thing if you're a photon. And if you're a photon, well, the remote future, and I'm getting myself a bit tangled up here, the remote future is on my transparency here. You can stretch it out, squash it in now, and it makes a nice smooth surface. So, okay, eternity is no time for a photon, and it's the conformal geometry again, because photons have no mass, and so they don't care about all 10 components of Einstein's equation metric. They're interested only in the 9. So the idea is maybe what went on before the Big Bang is the same sort of thing is going to go on in the remote future. And here I do need my transparency, which I've carelessly placed down somewhere here. And it should come into view very rapidly. Here we are. This was the one I had before. In fact, if this is projecting from above, I think I'll just do it this way. And here we have the two. And I'm going to suppose that what was before the Big Bang was the remote future of some other eon. That's where the eons come in. I'll show you the picture that I'll put it over here, I think. This is just combining the two procedures I've talked about, the Todd procedure, stretching out the Big Bang, and the other procedure, squashing down infinity. That's what's called conformal infinity. And they're both supposed to be nice surfaces. This one in the future is automatically nice. The one in the past is a huge restriction. It's the restriction we need to characterize the very low entropy in the universe, in the early universe. Now what I'm going to try and do is to suggest a picture to you. This is where it goes wild, if you like. That our present universe, as we understand it, that's just this thing I started the talk off with, this great thing here. Our present picture of the universe is but one eon in a succession of eons. That's this, and then there was one before and one after, where the conformal geometry, as long as there's no mass around here, the join is perfectly smooth. This joins onto this joins onto this, and the idea is that the universe is a succession of eons, one after the other. The conformal geometry continues smoothly from one to the next. Okay, that's a hypothesis, a lot stronger than simply the Weyl curvature hypothesis, and I think I want to end by saying two things about it. The first thing is something that you might immediately worry about with what I said, and that is, haven't I been worrying about the second law of thermodynamics? If the second law of thermodynamics says the entropy keeps on going up and up and up, what's happened to it here? I mean, how can it be going up and up and up and up if you've got these eons which are more or less the same as each other, perhaps one after the other? Well, this is something that did worry me for quite a while, and then it seemed to me, I'll tell you this sentence and a few sentences here, and I think I need to go back. Perhaps I do that first. Yes, I'll go back to that. I'll show you our eons here. I think I can get most of them, or a few of them on here. There's the eons. Perhaps putting it this way is better. And here we have the picture which I covered half of it up. And I covered half of it up because I didn't want to confuse you with the issue on the other side, which is what's known as the information paradox. The problem is, what happens to the information, in the sense of phase space volume, in the collapsing material? You see, it's all got squashed into this singularity in the middle, and all the degrees of freedom in that material seem to have got lost. Now, this was what Stephen Hawking maintained when he initially put forward the idea of this Hawking temperature and the disappearing of the black hole ultimately. And that was his view, and I'm happy with that view, although in fact my view was a bit stronger in that respect than his, but never mind. He then, later on, a few years ago, changed his mind and said no, in accordance with what a lot of other people tended to think, is that somehow magically all this information leaks out again. Perhaps it comes out in the pop at the end. That seems a little unlikely when you consider that a vastly huge galactic scale black hole or a tiny one produce the same sort of pop. So that's a bit hard to see. Or perhaps it's somehow in subtle correlations that go on outside here, which is what a lot of people believe. Maybe there's a final sort of nugget or remnant or something which carries all this information. Again, it's hard to believe that all the information in that vast 10 to the 10 solar mass black hole is concentrated in this tiny little ingredient here. Of course, there are hard things to believe which turn out to be true in physics, but that one I'm having a lot of trouble with. I think Hawking was right originally, so what I'm saying in this transparency, which I've got a bit crowded down here, I'm afraid. Let's bring that back again. It agrees with the young Hawking, I say, my idea. However, it disagrees with the change of mind he had. And the idea is that phase space volume somehow gets destroyed in the singularity as the matter falls in. And this has the effect that the zero of entropy gets reset. So there's never any effective violation of the second law. Everything goes along consistently with the second law, but every time the black holes disappear with a pop, your phase space shrinks. And it shrinks down in such a way that your formula for the entropy gets reset, the zero of entropy gets reset, so that by the time you've got to the crossover, all the black holes have gone, and the entropy, well, you see, you have to ask what you mean by entropy. It's the big phase space that has somehow got shrunk down and collapsed down, and so that the phase space volumes that appear in Boltzmann's formula are now much smaller than they were before. It's a subtle thing, and it's a sort of insidious thing in a way, but that's what happens according to this picture. Of course, all these things are things which need to be tested by observation, and that is my last point. Is all this that I'm trying to tell you science fiction, which it might indeed be, or is it true? And for that, we need observational evidence. And the major thing to look for, it seems to me, is the following. This is the crossover surface. That's the thing here. Let's say this one here. That's us. This is our Aeon. That's the one before. That's the crossover surface. It looks like a line here, but it's really a three-dimensional surface spanning the entire universe. I've drawn it here as a plane. That's the best I can do. Here's us in our Aeon looking back to the microwave background radiation. And in the previous Aeon, which I'm supposing is rather like, or was rather like ours, and that there were galaxies running around, there were galaxies in clusters. Every now and again, a pair of these galaxies would collide. Every now and again, when they do collide, their black holes would get close enough to each other that they would capture each other. They would spiral around each other for a while and then swallow each other up. That's the sort of expectation that we have that will happen from time to time. When that happens, there will be a burst of this gravitational radiation, which I described before, enormously energetic. When two huge black holes like that collide, the energy in that gravitational radiation will be a few % of the entire mass of those enormously massive black holes. So there's a huge amount of energy shot out in the form of these gravitational waves. They will be an almost instantaneous burst on the scale of things here. As this burst hits the crossover surface, it will cause a slight change in the temperature as we see it of the radiation. The picture I think that you need to have here is something like a pond, and it's been raining, and each little drop of rain causes a ripple coming out. Suppose it's raining now, and you see the little ripples coming out. Then it stops raining. The stopping of raining is when all the black holes have disappeared by Hawking evaporation. And then you look at it. Looking at it is the time of the crossover surface here. What do you see? Well, when you look at a pond, if it's been raining and it's just stopped raining, what would you see? You'd see a lot of ripples all over the pond. You wouldn't, at a casual glance, know that those ripples were essentially made up out of these circular effects from individual impacts of raindrops. However, if you did some clever statistics, you could work out if that is the major effect in the ripples. So what I'm saying here is that those individual raindrops are like these impulses, and you should be able to see an effect like this in the microwave background. Well, about 2 years ago, I was in Princeton, and I had a discussion with David Spergel, who is one of the world experts in analyzing the cosmic microwave background, and I said to him, has anybody ever seen an effect like this in the microwave background? And he replied, no, they haven't. But then he said, nobody's ever looked. And then he said, but it wouldn't be too hard to look and see. Well, you know, my expectations were jumping up and down like this. He said, give me a couple of weeks and I'll let you know. Well, I waited a couple of weeks and I didn't hear anything. And so after a couple of months, I emailed him and said, have you any more information about this? And he said he'd been rather busy, but he'd given it to a graduate assistant called Amir Hajian, and he thought he would look at it and see whether there's any evidence. Well, I'm going to have to cut a fairly long story down reasonably short because, okay, he sent me some information. At first you saw some spikes in the statistics which seemed to indicate something, and Spergel said, oh, you better look more carefully, they probably are spurious and don't mean anything. And indeed he looked, and indeed they turned out to be spurious. However, eventually he got down to some sending me some histograms, which for some strange reason have vanished on me here. These histograms were obtained by taking circles in the sky of different angular radius and then seeing whether the temperature as averaged over those circles was more or less than what you might expect from purely random statistical chance. And I think I can show you these. I can't see them very well. First of all, there were a lot of spurious effects having to do with the galactic plane and hot spots and cold spots which were out there and evidently didn't mean anything. And just as well they didn't, because they would have been bad news for me in other respects. But then there were curves like this. Now, I should say, I won't go and explain what these things are exactly. Each of these is for a different angular radius in the sky. And if this thing was a parabola, exact parabola, that would mean completely random. If it deviates from a parabola, that might mean something. And so you could see there are various humps here. They've got lots more of these curves here. And there was something like 500,000 different points I think they looked at. So quite a lot of statistics went into this. But there was a sort of systematic hump here. And I asked him, I said, what do those humps mean? This was Amir Hajian, the student, the graduate researcher. And he said, I don't know, probably there's something spurious. So I thought, well, that's not really good enough. I'd like to know what they are. So I made the suggestion that what he should do is have a look at the sky, but twist it. So you could take a small twist or a big twist. And the idea is that this twist doesn't change the area of what you're looking at, but it changes the shape. So it changes circular patterns into elliptical ones. So what you might expect is that with a little twist, if you see what it is without the twist, then with a little twist, the effect ought to start going away. With a big twist, it perhaps should go away completely. And so I was thinking there is no twist, a little twist, and a big twist. So he looked at this and came back and you could see an effect which was sort of systematically over a whole range from about, there were effects in other parts of the range, but from about 7 degrees radius to about 14 or 15 degrees radius. Systematically, you saw a tendency, very systematic, one, the next, and the other, in different colors. Green one, the furthest one out, the red one slightly in, and the blue one pretty well random. And so I thought, I got rather excited by that. And then I went back and I looked at the color coding. And this was his color coding. And I emailed him and I said, are you sure you've got the color coding right? It looks as though the green ones are the ones which were untwisted, the red ones with a bit of twist, and the blue ones with a lot of twists. That would be consistent. I can show you another picture here, which is showing you the same thing. As I say, over this whole range, and there are quite a few, I don't think about 20 or so different parabolas like this, and they all were in the same order, right over this range here. But there's the wrong amounts of twists. And this was completely baffling to me for a while. How on earth could that be? But then it occurred to me, maybe in some regions of the sky, remember the elliptical effects that distributions of mass had, some regions in the sky where there's too much matter or too little matter, and they cause the original circles to look elliptical. And that might be what's going on. And if, of course you could ask, why on earth that got anything to do with the twist that you've done? It'd just be pure fluke. But it may be that the twist, okay, in some places it's worse, in other places it's better. If you happen to hit a place where it's a lot better, that will cause a big effect here. If you happen to have hit a place where it's worse, you probably won't notice it. So it seemed to me that could be the explanation, that there really is an effect like this. But in addition to that, there are large irregularities in the matter distribution out there, and that might be what's going on. So I suggested, well, why don't you break the sky up into smaller bits, do the analysis again, and this and this and this. He said, well, I'm afraid I'm a bit too busy with applying for jobs, and my family back in Iran may have problems, and so on, and this, and quite reasonably. And it's a lot of work to do these things, so I understood it. But it was a bit of a shame not to know whether this was an effect which is really there or not. More recently, I became reminded of some work done by an Armenian astrophysicist named Gozagian, who had quite independently analyzed the sky and he deduced that there is distortion effects. There are distortion effects which he's actually measured. He says that are due to the irregular matter distributions between what you're looking at, the surface of the last scattering, as it's called, and us. So what you could do is take the Gozagian data, untwist the sky, so to speak, and then do this analysis again and see what happens. Well, what's the answer? I don't know. It hasn't been done yet, and I'm afraid I have to leave you in that sort of cliff-hanging position because nobody has yet done these observations to see what the effects are. But just watch this space. That's the best I can do, I'm afraid. Thank you very much.
Thank you, Roger, for such a fascinating talk. Listen to you is something like contemplating a piece of art, and not only because your transparencies are so beautiful, but also because, every great physical theory is a little, even great piece of art. And although your vision of the world is not yet full theory, only a good hypothesis, nevertheless, it has already a touch of beauty. And now we have some time for questions, comments. Please, if there is something.
Are there any differences between physical laws and constants between the particular eons? And the second one is, do you think that if we build a satisfying theory of consciousness, will it help in any way in developing the cosmology and trying to solve the problems of cosmology?
Now, that's an interesting question. And you might say, as Wheeler, in fact, suggested a long time ago, and Lee Smolin picked up on in his version, that in fact, in earlier phases of the universe, there might have been different values of the fundamental constants. And that's certainly a possibility. And it might be that things like the cosmological constant might be different or whatever. There is one tiny piece of evidence in favor of them not changing, but it could be only a small thing, and it doesn't affect your argument. And this is that if you plot out where we sort of are in this scheme, it's a bit hard to describe this, but if you imagine the pictures I've been showing you, well, you can see it here, and this means we're around about there in the expansion of the universe. In the conformal pictures, it means we're roughly 2/3 of the way up the picture. So we're about here in the diagram. Now, there is evidence that the correlations in the microwave background fall off at about 60 degrees in the sky. Now, one of the supports for inflation is that you have correlations over distant regions in the sky, which would be inconsistent without inflation or something like that. Now, in my scheme, the correlations would come about without inflation. They would come about because of events in the previous eon, such as these black hole encounters. Now, if it's right that they fall off beyond 60 degrees, that would be consistent with, you see, if we're about here, and let's suppose what the previous eon is sort of like ours, then that would mean that the black hole encounters don't tend to happen before about now. When I say now, that's a fairly broad region in this picture. So there wouldn't have been too many black hole encounters way back here. Now, if that's probably right for our eon, if that was also true in the previous eon, there would indeed, if they don't happen before about 2/3 of the way up, there would indeed be a cutoff at 60 degrees. So that's consistent with this previous eon existing and the constants of nature not really affecting when the black holes start to appear. Of course, there could be lots of other things. That's only one tiny piece of evidence, not very strong, but nevertheless some tiny piece of evidence to suggest that, well, it doesn't completely different in the previous eon. But it's a very interesting question, and maybe there is some way. There are lots of things about this, if it's right, which would give us abilities to test all sorts of things. One of them, in fact, is the Hawking evaporation, which in principle you might be able to see in the cosmic microwave background. I'm not quite sure how you do that, but in principle you could. Another thing, indeed, things like constants of nature, there could be some evidence that it would affect the distribution in matter or something, or the cosmological constant or something, in some way that would be in principle observable. So I think the general answer to your question is optimistic, that one has some potential, at least that we didn't have before, to see whether these constants of nature might actually be changing. But I have sort of two minds about it, because on the one hand it would be nice if they weren't changing, because then we could make many more predictions in this scheme. On the other hand, it would be very nice to get evidence to see whether they're changing or not. So it's potentially exciting. Of course, if the theory turns out to be completely wrong, that doesn't work. But it is a potentially exciting possibility. Thank you, yes.
And what was your second question? I don't remember.
The second question was?
The second question was that if we build any satisfying theory of consciousness, for example, something connected with quantum mechanics and so on,
well,
and microtubules, for example, and if it becomes satisfying so that we can fully explain the whole mental data and so on, that will it help in any way to develop cosmological problems, or will it be something that's referring to our brains, our lives, and that's all?
Well, it relates in a way to your other question, because some people would say, well, it's only because of some very remarkable coincidences that we can exist at all. I'm always nervous about these arguments, because all we know about is the kind of life we know about. And it could be there's some completely different kind of life which would like the constants of nature to have some quite different values. So I'm always a bit nervous about those arguments. the anthropic arguments, as they're called. But nevertheless, they are very relevant, and it relates to your earlier question. There's another issue which does relate also to my particular view on this issue, which is a whole new topic, a whole separate topic, of course, and that is that it depends on how quantum mechanics interrelates with Einstein's general theory of relativity. And I have the view that the puzzles, the fundamental puzzles of quantum mechanics, which have to do with the collapse of the wave function and how the measurement process fits in with the scheme of evolution that we know in quantum mechanics, how do we make sense of the measurement process according to the rules of quantum mechanics, and that, in my view, does have some relevance to consciousness, but that's a hugely different story. It does have relevance to this topic because it is related to the question of the second law of thermodynamics and how it's consistent with its scheme. You need to have the information loss according to the Hawking, I should have said the young Hawking view that information is lost. That violates unitarity. That goes against the standard view in quantum mechanics that no information is lost. Here, information has to disappear. And so that has relevance. But it's an indirect relevance to that question. So I think I can't say much about it.
Some other questions?
One question. You show this parabola,
yes,
which is the indirect measurement of the gravitational wave from the other eons before the Big Bang, as I understand.
I'm not quite sure I caught your question, but let me bring this picture up if I can find it again.
This parabola is the correlation at the cosmic microwave background, yeah?
Yes.
And this is the sign from these drops that you...
That's right. The black hole encounters will produce
gravitational wave.
A circle. Well, as we see it, there will be a circle where that gravitational radiation hit the...
Yeah, so it will be indirect measurement of the gravitational wave before the Big Bang, which we now see in the cosmic microwave background. And
yes.
First of all, it means that some kind of information can go through the singularity,
yes,
the primordial singularity. And this is not in opposite to what we know about the singularity as all from general relativity. So it's a problem for me to understand why the information can cross the singularity. Can you explain this more carefully?
Yes, I think you do have the usual view here, and it was my view before thinking about these things, that the Big Bang messes everything up. And so that no information could get through. But this is taking a different view of that. You see, if the Big Bang, as far as the conformal structure is concerned, is completely smooth, as I'm saying here, it goes against all quantum gravity theories and all sorts of things, but one can make a point here. And I should say that all quantum gravity theories have trouble with make sense of what the Big Bang is doing. If this view is right, that it is a conformally smooth situation, then massless radiation gets through. Not just gravitational radiation, that actually requires a slight explanation, but photons get through. So if you have certain regions where there is more light and other regions less light, that also will go through the Big Bang. You might think, how could it, you see, because it's so hot and messed up, but as long as there's no mass around, it goes through nice and cleanly. The gravitational radiation, it's a little more subtle, because the Weyl curvature goes to zero. You have to look at the equations more carefully. And what happens is that the gravitational radiation gets converted into a slight change in the conformal geometry of the crossover surface, and in a slight kick that it gives to the initial dark matter. So you have to look a little more carefully to see what the effect of gravitational radiation is. It's not actually in gravitational waves on the other side. It converts itself into a different form. But any other kind of zero rest mass radiation, yes, would get right through. So it's a strange, unusual view to what people had thought previously about what the Big Bang is. You think thermal, you say it's just a mess, it messes everything up. But that isn't true on this scheme. It really, information gets through.
I would pursue the same line of thinking.
Yes.
Between two eons,
Yes.
there is a sort of temporal hole, metric temporal hole.
There is a-
So in metric sense, you cannot say that what was before, because it's a presupposed time. The only thing which is left is conformal time, is a sort of causal ordering of events.
Yes, the thing is that I haven't shown you the equations here.
Yeah.
You have to go a little bit more carefully into how everything behaves. And there is a bit more information. Mm-hmm. To say it's just the conformal structure is not quite accurate.
Uh-huh.
It keeps track of time in a certain sense. It's not exactly clocks. Mm-hmm. It's more like, what would I say? A second derivative or something. There is, in the equations, there is something which keeps track of things across the color between one and the next. But it's not clocks in the ordinary sense. It's not the Einstein metric. That does go wrong on you. But there is something else which keeps track of time in a certain sense.
So, any other questions, please?
Can your theory help us to understand the puzzle of missing mass of the universe?
The missing mass?
Missing mass.
Yes.
80%.
Indeed. Well, I don't want to say too much here because I don't really know quite how to interpret it. But again, it follows on from Mikhail's question. You need equations to tell you how to go from a conformal factor into its reciprocal. That's what happens here. So you need an object which can carry that information across. And I've now slightly forgotten exactly what your question was. Can you just remind me?
Missing mass.
The missing mass, that's it. Yes. You find that you do need, for consistency, there has to be new mass created. In the form, the initial form it seems to have is a self-coupled scalar which is conformally invariant and massless. So it has to acquire a mass. In fact, a mass does get acquired after a little while. So you have some material which isn't anything that we have from standard particle physics. It just comes from the conformal factor. The fact that the conformal factor has turned upside down means that, in effect, there is something which starts off as being purely something to keep track of how you're scaling things and not any physical meaning. And on the other side, it becomes an actual field. And I'm postulating that that is the missing mass. Now, of course, it could be that the theory is right in other respects and wrong in that respect, and so on. But there is naturally something like new matter created at each new eon. And the old matter, the old missing mass, presumably gets largely swallowed by black holes, and one would need a theory of what happens to it. But there does have to be new mass. That's certainly true. You can't get away from that in this scheme. And so it could be that this new mass is what we call the missing mass now.
Can I ask? I would like to ask, if possible, two questions. First, what is the real nature of this boundary between two neighboring eons? Is it singularity at all? I ask this because some people believe that in Planck regime do not exist singularity at all, because do not exist space-time.
Yes.
So what is your attitude to this? And the second question is about what is your attitude to the so-called cyclic universe of Paul Steinhardt and Neil Turok, what was named also ectoporic universe. Yeah. It is similar a bit to you because there are cycles, but it seems to me that it is completely different. Do you agree, for example, that dark energy can act in such a way that is reversing expansion into contraction?
Yes, let me address the end first. There were certainly other theories, initially Veneziano, and then Steinhardt and Turok. Both those theories depend on ideas from string theory, and I'm certainly not appealing to that kind of idea here. As a general scheme, there's something in common between all these three types of model. what's basically different, at least from Steinhardt-Turok, is that I don't ever have a recontraction here. The universe is expanding. It just forgets it's expanding, if you like. And this becomes equivalent to a new Big Bang. It doesn't collapse. Whereas in Steinhardt-Turok, they say in after, 10 to the 9 years or something, the thing starts to come back again. That does not happen in this scheme. In their scheme, they'll still have black holes because the Hawking effect won't have taken place. And so that will mess up the Big Bang in ways that might be observable. So it's different. Veneziano's scheme I never fully understood. I don't fully understand the other one either, but Veneziano's scheme is a little more like this, in that he does have, I think, different scales of metric which are conformally related. So it's a bit more like this. But I think I would say that this scheme is independent, different from those, and has more detailed implications, because one can really say that this is a smooth transition governed by very precise laws that you can write down, in which the encounters between black holes would have a clear signal. So I think there are certain differences there. Now, there was a beginning to your question that you had.
Planck threshold.
Oh, yes, of course.
The nature of singularity.
Right. Quantum gravity.
Perhaps it is not existing at all because there is no local, only global features of the universe at this.
Now, this, you see, is a very different point of view. It differs very much from my own point of view as it was, say, more than 5 years ago, or 5 years ago, certainly. In that the usual view, which was my view, was that, yes, in the singularities in black holes and in the Big Bang, you need quantum gravity. Because quantum gravity is a place where general relativity tells you have curvatures which have radii smaller than the Planck distance. And so you should be looking at quantum geometry. And quantum geometry, oh, goodness me, there are endless theories, and most of them don't tell you anything. Some theories are worked up clearly enough that they tell you how to make a bounce of some sort through this. I've always found that a little unsatisfying, because if you have a bounce from a collapse to an expansion, you've lost the chance of explaining the low entropy. And it seems to me you want to have something quite different from that, something which is basically time irreversible. Whereas if you take any of these quantum gravity views, they're time reversible. And so how do you get this initial state from a collapse, which is a bit like the expansion on the other side, where your collapse would have to be aimed so carefully that all the Weyl curvature disappears by the time it reaches its final point. I just find that difficult to make sense of. The other point I should mention, yes, it goes against these conventional ideas of quantum gravity. When I say conventional, there is no accepted quantum gravity theory, but they all seem to say when radii of curvature get down to the Planck scale, you need some crazy idea of space-time. Now, what I'm saying here is that's the wrong point of view. What it is that leads you to crazy ideas of space-time is very small Weyl curvature, radii of curvature. And that's what you get in black holes. In black holes, the Weyl curvature goes wild. You get radii of curvature down at the Planck scale. Yes, quantum gravity, all sorts of things, crazy things happen. At the Big Bang, it's only the Ricci curvature which gets down to this. The Weyl curvature is zero. So there is no effect of this nature if it's the Weyl curvature, which is the gravitational field, which you say has to be at the level where quantum gravity effects are important. That's not happening here. It's only the source part, if you like. And so, okay, maybe that's wrong, but it's a reasonably consistent point of view. So I'm saying it's not quantum gravity in any of these senses in which space-time goes wild because of Planck scale curvatures, because it's only Ricci curvatures, and that you can conformally scale away. So the only problem is in the scale factor. So if you have a good classical way of dealing with the scale factor, and I have a proposal for that, then it's completely classically determined. Once you've got rid of the black holes, and there's quite a bit of time here, when I say time, I mean even on this conformal picture, you have quite a bit of region here where these classical equations will give you a completely deterministic evolution through the Big Bang. Okay, it might be wrong, but at least it's a proposal.
May I just go back to this question about the nature of the singularity? Is there a way, and does it have to be connected, for example? Is there a way that the universe would sort of branch out into, like going fork up and then link back again?
Not on this scheme. This scheme, I say there are several predictions, and one of them is that the topology of the universe does not change. And it doesn't branch. The only way it could branch would be through black hole singularities, but it has nothing to say about that. I'm just saying the black hole singularities do represent an end to space-time, and it gets crunched out of existence, and that's how the second law works. So on the scheme, okay, there could be a topology, an interesting topology to the universe as a whole. It could be open, could be closed, it could be glued up in some complicated way. That persists from eon to eon. It's always the same. So that's one of the few things I can say in this scheme.
Okay, so it seems to me that our discussion is about to be closed. Everybody who is interested in continuing that discussion, I invite tomorrow, Collegium Novum at 9 o'clock. Our symposium on Road to Reality with Roger Penrose continues. The talks are perhaps a little bit more technical than now, but in the couloirs you can always discuss and continue your intellectual pleasures. Thank you for tonight.